Welcome to the deep dive. Today, we're getting into something pretty fundamental about AI, specifically deep learning. You see these systems everywhere now, right? Powering language models, playing games, just incredible stuff.
Absolutely incredible.
But we usually think about them being trained like once, really intensely, and then they're done, deployed. What happens, though, when they need to keep learning continuously in a world that's always changing?
Yeah, that's the million dollars question, isn't it? Because the standard way we do deep learning, which is, fantastic for those train then deploy scenarios, it hits a wall. A surprising one, actually.
It hits a wall. How so?
Well, it seems like over time, these systems start to lose a really crucial ability, the ability to learn new things effectively. Their learning power kind of degrades.
Huh. Losing the ability to learn, that sounds problematic. And that's exactly what we're digging into today, right? This problem and maybe an innovative way around it.
Precisely. We're basing this deep dive on a really interesting academic paper. It's called Loss of Plasticity in Deep Continual Learning.
Okay.
The authors are Doher, Hernandez Garcia, Lon, Rahman Mahmood, and Richard Sutton, who many will know. It's proper research looking deep into this issue.
Right. So we're getting into the academic nitty gritty here, focusing on what they found and especially the new ideas they're proposing.
That's the plan. We want to unpack what loss of plasticity really means here technically. We'll look at the evidence they gathered, and they tested this across different areas like image recognition and even robotic simulation.
Okay.
Then we'll explore why they think this happens, what's going on inside the network. We'll also see how current standard techniques hold up or don't. And finally, the really innovative part, their proposed algorithm, continual backpropagation. We'll break down how it works and why it seems to solve the problem.
Sounds good. So let's start with that core finding. You said the systems lose their ability to learn. The paper puts it quite starkly, doesn't it?
It does. They state that essentially, standard deep learning methods, when they have to learn continually, gradually lose this plasticity.
Plasticity. Okay, we need to define that properly.
Right, they lose plasticity until they're basically no better at learning new things than a really simple, shallow network, like a linear model.
Wow. So you could have this huge, complex, deep network, but after learning for a while, it loses its deep learning edge for new stuff.
Exactly. And that term plasticity is key. It's specifically about the network's ability to learn new information or adapt to, say, new data distributions as time goes on.
So it's different from catastrophic forgetting because we hear about that a lot too.
It is different, yeah. Though related, catastrophic forgetting is about the network losing old information, forgetting what it learned before. Loss of plasticity is about losing the ability to learn in the future. The network sort of ossifies, it becomes rigid.
Okay, so it's not just forgetting the past, it's becoming unable to learn the future. That's a big deal. And you mentioned they showed this wasn't just a one-off, they tested it broadly.
Oh yeah, very systematically. They didn't want this to be some niche artifact. They used different network types, different standard learning algorithms.
And different kinds of problems.
Right. They use things like continual ImageNet, basically a long stream of different image classification tasks,
Okay.
and class incremental CIFAR 100, where the network has to keep learning to recognize new types of images that are added over time.
So sequential learning tasks. What else?
They also went into reinforcement learning. They had this simulated ant robot learning to walk,
Ah, okay.
and they tested it both when the physics changed, like the friction on the floor varied over time that's non-stationary.
Makes sense.
But crucially, they also showed plasticity loss happened even when the environment stayed the same, just over very, very long training times. So it's not just about the world changing.
That's interesting. So even in a stable world, just learning for long enough can cause this.
It seems so. And they also used a benchmark called online permuted MNIT. It's computationally a bit cheaper, but still really effective for showing the problem. Basically, for each new task, they scrambled the pixels of the MNIT's handwritten digits randomly.
So the network constantly has to figure out new features.
Exactly. It forces continuous adaptation.
And across all these different tests, images, robots, scrambled digits, what was the consistent finding when using standard methods?
The pattern was pretty undeniable. Standard algorithms, even popular ones, would start off fine, but their ability to learn later tasks or just to keep performing well after a long time in RL would degrade, sometimes significantly.
Degrading how much?
Well, in some cases, performance on new tasks would drop right down to the level of a simple linear model, just like the paper climbed. Or in the RL tasks, the learning ability could just collapse entirely after a while. I really showed that initial good performance doesn't guarantee the network can keep learning.
Okay, that paints a pretty clear picture of the problem. If we want AI that learns throughout its life, this is a major hurdle. So the next big question is why? What did the paper find is actually going wrong inside the network?
Right, this is where their investigation gets really interesting. They identified three key things happening internally that correlated strongly with this loss of plasticity. And they argue these aren't just symptoms, they're likely contributing causes.
Okay, what's the first one?
The first is an increase in what they call dormant or saturated units. Think about the neurons in the network.
Mm-hmm.
In networks using real U activation, which is super common, a lot of these units can just become dead. They output zero no matter what the input is.
Zero output, so they're not doing anything.
Exactly. They stop contributing, no gradient flows through them, so they can't learn or change. They're just stuck. For other types of units, like sigmoid or tan, they can get saturated stuck at their maximum or minimal value. Again, the gradient becomes tiny, so learning effectively stops for those units too.
So bits of the network just switch off, functionally speaking.
Pretty much, they lose their individual plasticity. That's the first thing. The second is an increase in the average magnitude of the weights.
The connection strengths get bigger.
Yeah, the absolute values tend to grow as training goes on and on. The paper suggests this might make the optimization landscape the sort of surface that the learning algorithm is navigating more complex and jagged, making it harder for gradient descent to find good updates for new learning.
Okay, so bigger weights might make learning harder or slower later on. What's the third correlate?
The third one is a bit more technical, a drop in effective rank.
Effective rank. Okay, break that down for us.
Think about layer in the network. The effective rank basically measures how diverse or non-redundant the patterns are that the units in that layer are representing.
Uh-huh.
A high effective rank means lots of units are contributing distinct, useful information. The network's internal representation is rich, flexible. A lower effective rank means the information is kind of compressed. Many units are doing similar things, becoming redundant. The representation space becomes less diverse, less flexible.
So it's like the network runs out of unique ways to represent things internally.
That's a good way to put it. And they found that as plasticity drops, so does this effective rank. The network's internal language becomes poorer, less able to express solutions for new problems it hasn't seen before.
Okay, so let me recap the why. We've got units becoming dead or saturated, weights getting large and potentially hindering optimization, and the internal representations becoming less diverse and flexible. It's like the network starts out valuable and full of potential, but standard training makes it rigid and constrained over time.
That captures it really well. The optimization process itself seems to erode the very properties that allowed learning in the first place.
Which leads to the question, are there tools we already use in deep learning that can help? Did they test things like different optimizers or regularization techniques?
They did, and this is where some results were quite surprising, maybe even counterintuitive for people working in the field.
Oh, like what?
Well, they found that some really common methods, things like the atom optimizer,
Everyone uses Atom.
right, atom, and also techniques like dropout and certain kinds of normalization, these things actually seem to make the plasticity loss worse in their experiments compared to just using basic SGD.
Wait, worse. But those are supposed to improve training.
I know. It's surprising. The thinking is perhaps they optimize really well for the current task or for generalization in a fixed setting, but they do it in a way that inadvertently speeds up this process of the network becoming rigid, reducing diversity, or increasing dormant units faster. The paper specifically calls out Adam's negative effect on effective rank and dormant units.
Wow. Especially since Atom is so common in reinforcement learning, where you'd think adaptability is key.
Exactly. It's a significant finding. However, they did find some existing methods offered a bit of help, just not a complete solution.
Like what?
L2 regularization, adding a penalty to discourage large weights did help a bit. It kept the weight magnitudes down, which fits with their finding that large weights are bad for plasticity.
But it wasn't enough.
No, it didn't fully solve it. It didn't really stop the units from dying off or the effective rank from dropping as much.
Okay. Any others?
They also looked at shrink and perturb. That's basically L2 regularization, plus adding a tiny bit of random noise to the weights constantly.
Injecting some randomness.
Yeah, and that performed better than just L2. It helped with weight growth and seemed to reduce the number of dead units, probably thanks to the noise shaking things up a bit.
But there's always a but.
Well, they found it was quite sensitive to getting the settings just right, and importantly, it still resulted in a lower effective rank compared to what you'd get if you just started fresh. So better, but still not maintaining that full representational diversity.
So the pain away seems to be that our standard toolkit is lacking here. Some things don't help, some even hurt, and the ones that help a bit aren't hitting the root causes effectively enough.
That's exactly the conclusion they drew. It really motivates the need for something new, something specifically designed to maintain plasticity.
Which brings us to their main contribution, this innovative algorithm, continual backpropagation.
Yes, this is their novel proposal. It's designed precisely to tackle this plasticity loss head on and hopefully allow networks to learn continually without degrading.
And the core idea sounds deceptively simple. It's basically normal backpropagation, but with a twist.
It is elegant, yeah. You still have the standard gradient descent learning, but you add a small controlled amount of non-gradient change. Specifically, at each learning step, you randomly reinitialize a tiny fraction of the units in the network.
Reinitialize, like setting their weights back to small random values as if they were new.
Exactly, like hitting a mini reset button on a few units. And this is crucial, it's not just any units, it's a selective reinitialization.
Selective how?
They developed a way to identify units that seemed less useful. They calculate something called contribution utility for each unit.
Contribution utility, what does that measure?
It's trying to estimate how much a unit's output actually impacts the next layer's computation. It looks at the unit's activation level and the strength of its outgoing connections. If a unit consistently has low utility, meaning it's not activating much or its outputs aren't strongly influencing the rest of the network, it becomes a candidate for reinitialization.
Okay, so you find the units that aren't pulling their weight, so to speak, and you replace them with fresh recruits.
That's a great analogy. You're replacing the potentially stale or irrelevant units with new, randomly initialized ones that have the potential to learn something useful for whatever the network needs now or might need soon.
Does it protect the new ones so they don't get immediately wiped out if they don't contribute right away?
Yes, good point. They have a maturity threshold. Newly reinitialized units get a grace period. They're not eligible for reinitialization again for a certain number of steps, giving them a chance to integrate and start contributing.
This whole idea of selectively replacing less useful parts with random new ones, it feels like it connects to older ideas in AI, maybe even biology.
Absolutely. And the paper makes this connection explicit, which is a key part of its academic contribution, especially focusing on the innovation here. They frame it as combining gradient descent with variation and selection.
Like evolution.
Kind of, yeah. You have variation, the random reinitialization, and selection, keeping units that develop high utility while replacing low utility ones. They draw lines back to classic AI concepts, like Oliver Selfridge's Pandemonium from 1959.
Pandemonium.
Yeah, it was this idea of demons shouting based on features they detected, and a master demon listening to the loudest shouts, kind of generating and testing features. It connects to a whole history of AI research looking at search, generate, and test and representation learning, including foundational work by Mahood and Sutton themselves. So it's taking this modern powerhouse, gradient descent, and integrating this older but powerful principle of continually generating and selecting representations.
So the goal is to constantly inject new potential into the network, keeping it from getting stuck in a rigid state, always maintaining that diverse pool of resources it started with.
Precisely. It's about fighting that natural tendency towards rigidity by continually refreshing the representational building blocks, keeping the network adaptable.
Okay, theory sounds compelling. It's an innovative blend of ideas. How did it actually perform in their experiments? Did continual backpropagation live up to the promise?
The results they show are, frankly, quite striking. Across the different benchmarks, it consistently demonstrated a strong ability to maintain plasticity where the standard methods failed.
Tell us more. What happened in the image tasks?
On continual ImageNet and the class incremental CIFAR 100, the networks using continual backpropagation basically showed little or no drop in performance as they learned more and more tasks. They maintained high accuracy throughout.
Wow.
And crucially, looking inside the network on SOFAR 100, it stopped the units from dying off and kept the effective rank high. It directly counteracted those internal problems we discussed.
So it fixed the underlying issues.
It seems so. And on continual ImageNet, there was another cool finding. It actually learned the later tasks faster than if you trained a completely new network from scratch each time.
Faster. How?
It suggests that while it's staying plastic, it's also retaining some generally useful knowledge or structure from the earlier tasks, giving it a head start, so full plasticity and some positive transfer.
That's really impressive. What about the robot ant, the reinforcement learning?
That's often considered a harder test for continual learning. There, they combine continual backpropagation with a little bit of L2 regularization, and it significantly outperformed the standard RL algorithm PGO. It maintained high performance basically indefinitely, even when the environment changed or just over very long runs.
And internally, did it fix the issues there too?
Yep, kept dormant units low, stable rank high, weight stable. It seemed to mitigate all three correlates successfully, even in that complex RL setting.
Okay, and the permuted M&Ice dust, the scrambled digits.
That was maybe the clearest demonstration over a very long timescale. Continual backpropagation just showed stable, non-degrading performance across hundreds of tasks. And again, it effectively addressed all three internal issues. Almost no dead units, weights didn't grow out of control, and the effective rank stayed high the whole time.
So it really seems to keep the network internally healthy and flexible like it was at the start, while still allowing the normal learning process to happen.
That seems to be the case. It's like the targeted randomness just counteracts the rigidity that gradient descent alone seems to induce over long periods. The paper's conclusion is pretty strong. Plasticity loss isn't inevitable. It's just that standard training lacks this crucial component for maintaining variability. Continual backpropagation provides that missing piece.
This feels like it could be a really big deal for where AI goes next. If systems can actually keep learning effectively forever, what does that unlock?
Oh, it's huge. Think about robots operating out in the messy, unpredictable real world for years, or self-driving cars, or scientific AI trying to make sense of constantly streaming data from experiments or observations. If they can genuinely learn and adapt throughout their entire existence without needing complete retraining, it opens the door to truly lifelong evolving AI agents.
Right. So, how does this fit into the bigger picture of continual learning research? You mentioned stability versus plasticity earlier.
Yeah, that's an important distinction. A lot of continual learning research focuses on stability, how to stop the network from forgetting old things, catastrophic forgetting. This paper is really laser focused on the other side, plasticity, maintaining the ability to learn new things.
So, continual backpropagation helps plasticity, but does it help with forgetting?
Indirectly, maybe, by keeping the network flexible, it might be better able to accommodate new information without overriding old stuff as drastically. But continual backpropagation itself doesn't have explicit mechanisms to protect specific old memories. The authors definitely point out that combining their method with techniques specifically designed to prevent forgetting is a really important direction for future work. You'll likely need both.
Makes sense. You need to remember the past and learn the future. Did they mention any other interesting theoretical connections? You mentioned the lottery ticket hypothesis earlier.
They did briefly, yeah. It's speculative, but they suggest the drop in effective rank seen in standard continual learning might relate to the lottery ticket idea. Maybe the standard training process destroys or make inaccessible those winning ticket subnetworks that are crucial for future learning. Keeping the rank high, as continual backpropagation does, might preserve a richer pool of potential tickets. It's a neat potential link.
So, what's next? Where does this research point? What are the open questions?
Well, refining that contribution utility measure is one thing, making it less heuristic, more principled, exploring different ways to do the reinitialization, maybe tweaking connections instead of whole units, or using different random distributions, and fundamentally just getting a deeper theoretical grip on what exactly about that initial random state is so important for plasticity, and how we can best preserve it algorithmically.
Okay, so let's try and wrap this up. We've taken a deep dive into this, maybe under the radar, but really critical challenge for deep learning. How systems lose their ability to learn over time in continual settings. We've seen the why, those internal changes like dead units, big weights, shrinking effective rank.
Right? The network becoming rigid.
And then we explored this really innovative solution, continual backpropagation, which seems to tackle the problem head on by borrowing ideas from variation and selection, injecting controlled randomness to keep the network flexible and, well, plastic.
It really drives home the point that standard deep learning, as powerful as it is, might not be inherently equipped for learning that never stops. But by adding mechanisms specifically designed to maintain internal diversity and adaptability, like this selective reinitialization, we might actually get there. We might be able to build AI that can truly learn and adapt indefinitely.
It definitely makes you think. So here's something for you, the listener, to ponder. We often talk about AI needing more data, bigger models. But maybe one of the biggest leaps will come when AI can truly learn continuously throughout its entire operational life. If an autonomous robot or a scientific discovery system, or even just your personal digital assistant, could maintain its learning edge forever, adapting and growing with every new experience. How fundamentally does that change what AI can ultimately become? What possibilities open up when learning truly never has to stop?